I'm Director of the Georgia Tech Honors Program, and I'd like to welcome you and thank you for coming to this evening's Karlovitz lecture with our friend Dr. Alan Lightman. This lecture is the first formal collaboration between the Georgia Tech Honors Program and the College of Sciences, and I hope this will be the first collaboration of many. And of course, a collaboration of this sort means that people do have to collaborate, and I want to thank those folks who have collaborated to make this event possible tonight. From the College of Sciences, I especially want to thank the Director of Administration, Jan Brown, who can't be with us this evening, but also Associate Dean Kent Bearfield, back in the back, and of course Dean Paul Houston, whom I'll introduce more fully and effusively in a few minutes. And from the Honors Program, I especially want to thank our Academic Advisor, Nicole Leonard, and the Associate Director, Monica Halka. In fact, I especially want to thank Monica Halka for helping to organize several student-faculty reading groups to discuss Alan Lightman's fascinating book, Einstein's Dreams. One of my students, who happens to be here tonight, I won't identify said student, wrote and said to me, she said, "First of all, Dr. Lightman's book is phenomenal. And after that, you don't need a second of all." There it is. That says it all. And I think that was really a fairly common response among a lot of the students who read and discussed this book. Now, Monica Halka and Nicole Leonard have worked with me long enough to know some of my more endearing and annoying habits, and so I'm sure they'll be impressed when I say that tonight I'm making the supreme sacrifice. I'm turning off my BlackBerry. And I will ask all of you to turn off your BlackBerries, your cell phones, whatever electronic noisemakers you may have with you. Certainly if I can do it, you can too. Well, before I introduce Paul Houston, I want to say a word about another dean, a dean for whom this lecture series is named, and that's Les Karlovitz. Les Karlovitz, who died in 1990. When I came to Georgia Tech as an assistant professor, Les Karlovitz was dean of the old College of Sciences and Liberal Studies. That was the predecessor to the College of Sciences and to the Ivan Allen College of Liberal Arts. And Dean Karlovitz, I think it's fair to say, was an imposing, almost intimidating presence who could make an assistant professor tremble at times, or at least one assistant professor that I know very well trembled in his presence. But Les Karlovitz was also a man with a very wide intellectual reach. It was Les Karlovitz who started the student-faculty summer reading program, which has now, I'm happy to say, been revived. And he'd be very happy to know, I think, that students and faculty members are still getting together to read and discuss a good book, as they have done in the last few days in preparation for this event tonight. It was also Les Karlovitz who sponsored fairly regular college-wide colloquia, where some faculty member would come and talk about his or her research, and then we would all enjoy a really good cocktail party on the dean's budget. And the critical terms there, Paul, are a really good cocktail party and dean's budget. So, no, but Les Karlovitz liked to bring people together, and I think he'd be happy to see us all together here tonight. I think he'd also be happy to know that the College of Sciences is still in very good hands with a still new dean, Paul Houston. Paul may not feel so new anymore, but in the geologic time of Georgia Tech, he is. I happen to be on the search committee that recruited or helped recruit Paul Houston to Georgia Tech. And I've got to tell you, it was one of those rare times when you finished working on a committee and you said to yourself, well, that was worth it. That was time well spent. I think we did very well in this particular case. Paul came to us from Cornell, where he spent essentially all his academic career. He received his PhD in chemistry at MIT, where Professor Lightman is now. Paul then did a postdoc at Berkeley, and then went to Cornell in 1975 as an assistant professor of chemistry. And there he rose through the proverbial ranks to become chair of the Department of Chemistry, the senior associate dean of the College of Arts and Sciences, and along the way he was also named the Peter W. Debye Professor of Chemistry at Cornell. And I think in addition to being a strong scholar and able administrator, Paul Houston is a good and genial man. And I'm very happy to have him here at Georgia Tech, and very happy to give him the honor of introducing our guest this evening. So I'll give to you Paul Houston.
Thanks very much, Greg. It's an honor to be able to make this introduction tonight. Let me begin this introduction by discussing a more general topic. While there has been a great deal of focus over the years on the public's understanding of science, those trained in science and engineering might well be reminded that their own understanding of the public is also an important issue. What lies behind the public response to new advances and discoveries? Public concerns arise not only from ignorance sometimes, but also from legitimate worries. Some of these are reinforced by historical examples. Science and technology need not only to provide new options for the public, but also to help guide the public in their appropriate use. We cannot do this without a clear understanding of the broader issues facing humanity. For this reason, the American Academy of Arts and Sciences is currently sponsoring a major study on scientists' understanding of the public, advised by the likes of Charles Vest of the National Academy of Engineering and Neil Lane, former director of the National Science Foundation. The American Academy would do well to engage another of its own members in this effort, our speaker today, Dr. Alan Lightman. In a long list of best-selling books and cogent articles, Dr. Lightman has provided a connection between the world of science and the world we all face as part of the broader human endeavor. The history of how he became a leader in this effort is an interesting one. Alan Lightman was born in Memphis, Tennessee in 1948, the son of Jean Gerritsen, a dancing teacher, and Richard Lightman, a movie theater owner. He graduated from Princeton in 1970 with a major in physics and received his PhD in theoretical physics from Caltech 4 years later. He was a postdoc at Cornell University, and he taught at Harvard University. His scientific research focused on relativistic gravitational theory, the structure of accretion disks, radiative processes, and stellar dynamics. His contributions led to many honors, including fellowship in the American Physical Society and in the aforementioned American Academy of Arts and Sciences. He was a past chair of the High Energy Division of the American Astronomical Society. As impressive as all of these accomplishments are, they are actually not why he has been invited to speak to us tonight. In 1981, Lightman began publishing essays about science, the human side of science. His articles appeared in Science, The New Yorker, Smithsonian Magazine, and many others. Books of essays soon followed. In 1989, he was appointed Professor of Science and Writing and Senior Lecturer in Physics at the Massachusetts Institute of Technology. Shortly later, he headed a program in Writing and Humanistic Studies at MIT, and he helped to create a new communication requirement. Get this, students. It required one semester in, one course in writing or speaking in each of a student's 4 years. In 1995, he became the John E. Burchard Professor of Humanities at MIT, and in 2001, he co-founded the graduate program in science writing. The writing that Lightman is best known for is his fiction. Good Benito is about a physicist who finds that the order and beauty of the equations he solves are incomplete and inadequate for confronting the contradictions he sees in light. Ghost is about David, who works at a mortuary and there sees something that he cannot understand. It explores the divide between the physical world and the spiritual world, between science and religion. And Einstein's Dreams, which many of us have read or reread this semester, considers fanciful dreams in which Einstein imagines new worlds where time flows backwards, is circular, is still, or speeds up as one moves away from a center. Einstein, the epitome of rational thought, is in Lightman's view also a dreamer, a person who experienced intense loneliness, a scientist who might have failed to achieve what he did without his sometimes irrational personal commitments and passions. Lightman reminds us that human beings have a, quote, wondrous capacity for being both rational and irrational, detached and passionate, deliberate and spontaneous, and that they seek questions with answers and questions without. He challenges us, those of us in science and engineering, to understand these juxtapositions, and he reminds us in the end that we are all human. Please join me in welcoming Alan Lightman to Georgia Tech.
Thank you for that wonderful introduction, Dean Houston. I want to thank Monica Halka for being involved with inviting me here. I want to thank Professor Greg Nobles, and I'm very honored to be at one of the nation's leading institutions of science and technology. I actually have several special connections to Georgia Tech. My wife, Jean, grew up here. Is this loud enough? Can you hear me in the back? Yeah. Good. My wife grew up in Atlanta, and I am a Southerner myself. I grew up in Memphis. And finally, the director of your honors program, Professor Gregory Nobles, was a classmate of mine in college. So I feel a lot of fondness for Georgia Tech. Ever since I was a young boy, my passions have been divided between science and art. And I have been very lucky in my life to have made a career in both as a physicist and a novelist. But there's always been a rumbling in my stomach, a kind of tension between these two worlds. And I think that's been the source of my creativity, actually. In childhood, I wrote dozens of poems, and in verse, I expressed my questions about death, about loneliness, about my admiration for a plum-colored sky, my unrequited love for 14-year-old girls. This was when I was 14. And there were overdue books of poetry that littered my second floor bedroom. Reading, listening, even thinking, I was mesmerized by the sounds of words. Words could be sudden like jolt, or words could be slow like meandering. Words could be silvery, they could be prickly to touch, they could be loud like a trumpet. And by some kind of magic, words could create scenes and emotions. And I remember that when my grandfather died, I wrote a poem about expressing my feelings, and about a month later I read it to my grandmother, and she listened and she cradled my face in her hands and said to me, "That's beautiful." And then she began crying all over again. And I wondered how black marks on a white sheet of paper could create that kind of power and force. Between poems, I did scientific experiments, and these I conducted in a cramped little laboratory I made out of a closet connected to my bedroom. And in this laboratory, I kept test tubes and beakers and beautiful glass flasks and coils of wire and resistors and capacitors and photocells and batteries and things like that. I just loved to build things. I loved to do experiments. Around the age of 13, I built a remote control device that could turn on the light in any room of the house from any other room. And this totally awed my 3 younger brothers. It was important to have an audience for these things. After seeing the Frankenstein movie, I built a spark-generating induction coil that required weeks and weeks of winding about 2 miles of wire around an iron core. In some of my scientific investigations, I had a partner named John, who was a year older than me. John was my best friend, and John was very skinny. He had this hyena-like laugh, which he still does. I visited him a few weeks ago. on the occasion of his 60th birthday. But John did not share my interest in poetry or the higher arts. John thought all of that was a waste of calories. John was just interested in practicality. But he was really a genius with his hands, and we would sit on the floor of his bedroom in his house listening to a Bob Dylan record. This would be in the mid-60s, and John never saved the directions that came with new parts, and he never drew diagrams before he made a circuit, but whenever he would build something, it would work. It was never pretty, but it worked, and usually it worked better than my inventions and gadgets. Well, it was with my rocket project that my artistic and scientific interests first collided. Ever since the launch of Sputnik in October of 1957, I had been really mesmerized with the idea of sending a rocket aloft. I imagined building the thing, I imagined the blast off, I imagined the smoke coming out of it and the trajectory and space. All of that just fascinated me. By the age of 14, I was experimenting with my own rocket fuels. And for the ignition of the rocket, I used the flash bulb from a Brownie camera. Now, the older ones of you will remember the Brownie cameras and the kinds of flash bulbs that were made in those days. The great asset of a flash bulb from one of those early cameras was that you could ignite the flash bulb with two wires on the two ends of it to the two leads, which you could then trail the wires to your command bunker a safe distance away. And the high heat of the flash bulb stuck into the fuel chamber would ignite the fuel. So it was a perfect way to ignite the fuel of a rocket. The body of the rocket I made from an aluminum tube. The container that held, I guess, the launch pad, I would say, was a Coca-Cola case filled with concrete and a metal strut sticking out of it. And the rocket had red tail fins. It was a beautiful thing to behold, just beautiful. So I invited my younger brothers and some friends from the neighborhood to come watch the launch of this rocket, which occurred one Sunday morning at dawn at the Ridgeway Golf Course in Memphis. John was not the slightest bit romantic and didn't see anything useful about rockets, so he decided to stay in bed that morning. But still, I had a good turnout from the boys in the neighborhood. I had calculated from the weight of the rocket and the thrust that it should rise about half a mile high, and so a lot of the boys brought binoculars. Well, then it was time to launch the rocket. So from my command bunker, I closed the switch. The flash bulb went off. The fuel was ignited, and a sudden whoosh, the rocket took off. It was a beautiful launch, but then after rising only a couple of hundred feet, the rocket did this sickening curve and crashed. The tail fins had come off, and then I realized that instead of riveting on the tail fins as I should have, I had glued them on. The rivets had appeared too ugly to my eye. So I had sacrificed reality for aesthetics. And later on, I learned that I was not the first scientist in history for whom beauty had ultimately succumbed to reality. For centuries, as many of you know, astronomers thought that the orbits of planets were circles. Circles because it's the most perfect geometric shape. It's in many ways the most beautiful, most elegant geometrical shape, and it was very pleasing aesthetically. But then the observations of Tycho Brahe in the 16th century and the work of Kepler showed that the orbits were ellipses and not circles. There was another very beautiful idea in physics in the 1930s and 40s called parity conservation, which says that the right-handed and left-handed versions of all objects and processes are identical, as if you were looking in a mirror. The mirror image of everything you see also exists. And that is a beautiful idea. It seems compelling, it seems plausible, it seems that that's the way nature should be. But that idea was proven wrong by experiments in the 1950s. So nature is not always as beautiful as we would like it to be. When my scientific projects went awry, I could always find fulfillment in mathematics. And I imagine that all of the students here like mathematics as I did when I was 13, 14, 15 years old. And I remember that when my teachers would give me math homework, that I would save the math problems till last before bedtime, like a dessert of chocolate cake awaiting me after a long, dutiful meal of history or Latin. Then I would devour my cake. In geometry, I loved drawing the diagrams. I loved the inexorable relations between angles and lines. And in algebra, I loved the abstraction. I loved letting the x's and y's stand for the number of pennies in a jar or the height of a mountain, and then solving the equations one logical step after the other. I love that kind of certainty in mathematics, that purity. In mathematics, as opposed to the social sciences, you were guaranteed an answer, and when you got that answer, you knew that you were right, unquestionably right. The area of a circle is pi r squared, and there's no arguing about it. Mathematics contrasted strongly with the uncertainties and the ambiguities and the contradictions of people. People confused me. My mother sometimes said cruel things to me and my brothers, even though we knew that she loved us. My Aunt Jean continued to drive recklessly in her MG sports car, even though everybody in the family told her that she would kill herself in that car one day. We had a wonderful woman named Blanche who worked for our family for many, many years, and she finally left her husband because he had been abusing her for years. And then for many years after, she spoke of her husband with affection. And I wondered, how does one make sense out of these apparently contradictory words and actions? Well, now, years later, after having lived in the communities of both scientists and artists, I have some tentative ideas to these questions. So I wanted to tell you tonight a little bit about what I've learned about the differences in the way that scientists and artists view the world, their different conceptions of truth, and also something about the many similarities. A big distinction that I've found between physicists and novelists, and my field of the arts is the novel, and I could extend this more generally to scientists and artists. A big distinction that I've found between scientists and artists is in what I'll call the naming of things. And roughly speaking, the scientist tries to name things, and the artist tries to avoid naming things. To name a thing, you've gathered it, you've purified it, you've distilled it, you've attempted to identify it with some kind of clarity and precision. You put a box around the thing and said what's in the box is a thing and what's not is not. For example, consider the word electron, which is a type of subatomic particle. As far as we know, all of the zillions of electrons in the universe are identical. There's only a single kind of electron. And to a modern physicist, the word electron means a particular equation. It's called the Dirac equation. And that equation summarizes everything that we know about an electron. The way that electron will deflect in a magnetic or electric field, the precise energies of electrons and atoms, every aspect of an electron is governed and predicted to many decimal places by the Dirac equation. And in a sense, that is what the word electron means to a physicist. And in fact, every physical object in the universe, the scientist wants to be able to express with this kind of precision. To a scientist, it is a great comfort and a feeling of power and a sense of control of the world around you to be able to name things in this way. But the objects and the concepts that the novelist deals with cannot be named in this way. The novelist might use the word love or the word fear, for example, but those words don't really summarize much or convey much to the reader. For one thing, there are 1,000 different kinds of love. There's the love that you feel for a mother who writes you every day your first summer away from home at summer camp. There's the love that you feel for a mother who slaps you when you come home from the prom drunk and then embraces you. There's the love that you feel for a man or a woman that you've just made love to. There's the love that you feel for a friend who calls you up when you've just split up from your spouse or your boyfriend or girlfriend, and on and on. But it's not just the different kinds of love that prevent the novelist from truly naming the thing. It's that the sensation of love, the particular sensation out of the thousands of different kinds of love, must be shown to the reader, not named, but shown through the actions of characters. And if love is shown rather than named, then each reader will experience it in her own individual way. Each reader will draw on her own adventures and misadventures with love. Love means one thing to one person and a different thing to another with different life experiences. Every electron is identical, but every love is different. And the novelist does not want to try to eliminate these differences. The novelist does not want to try to distill the meaning of love into a single, precise meaning as in the Dirac equation, because, first of all, no such distillation is possible. And even to attempt such a distillation would destroy that magical, delicate, participatory act that happens when a good reader reads a good book and participates in the creative experience. In a sense, a novel is not completed until it is read by a reader, and every reader completes the novel in a different way. Now, there's more to this business of naming and not naming than just the sameness of electrons and the varieties of love. It's that even a single reader can change from one moment of her life to the next, so that her experiences and her relationship to the world are constantly changing, and a novel, a story, a character, or even a single word can change in their meaning over time. Let me give another illustration of the difference between naming and not naming, and let me make the far-fetched analogy. Let me represent science by expository writing. And that may seem a little strange to you, but there are some similarities between expository writing and the scientific enterprise. It's an organized activity. In expository writing, you can decide what kind of arguments you want to make. You can begin doing research. You can organize your material. You can make an outline. You can lead your reader in a logical path from the beginning to the end of the argument. And we all learn, and we should learn this about 7th or 8th or 9th grade, that in expository writing, it is good form to start each paragraph with a topic sentence. And what a topic sentence does is it names the idea of the paragraph. It tells the reader how to organize his thoughts, how to begin thinking about what he's going to learn in that paragraph. But in fiction writing, and I made this mistake many times myself, in fiction writing, a topic sentence is fatal. It's fatal. Because in fiction writing, what you're trying to do is you're trying to get your reader to join, to come into the scene, to feel it, to smell it, to hear it, to be there in the small room with the two characters talking. You want your reader to let go and be carried off to the place that you're creating. And every reader will travel differently depending on his own life experiences. Telling your reader right at the beginning of the paragraph how to think about the experience will totally cancel the trip. With a topic sentence, you're not leaving room for your reader's own imagination. And your reader's imagination is everything in fiction writing. Sometimes I think the difference can be stated in terms of the body, that in nonfiction writing and expository writing, you want to go first to your reader's brain, and in creative writing and fiction writing, you want to bypass the brain and go to the stomach or the heart. There's a pattern of thinking that's closely related to naming, and that is the tradition of framing problems in terms of questions and answers. Scientists usually work, I think they always work, by finding interesting problems and then breaking those problems into smaller problems that have definite answers. Science, of course, is constantly revising itself. It's constantly discovering new data, new theories, and it must react to the new things it discovers. But at any given moment of time, any scientist is working on a problem that he or she feels has a definite answer. And in fact, most of the game of science is to pose problems with enough clarity so that they have definite answers. And then the world is built piece by piece from these solvable problems. For example, a typical scientific problem might be, how does a living organism pass on the instructions to create a new organism to its descendants? That's a question. And one sub-question would be, where in the living organism are those instructions stored? That's a definite question with a definite answer. Another sub-question would be, what is the molecule that carries those instructions on it? That's a definite question with a definite answer. What is the structure of that molecule? Another definite question with a definite answer. And we scientists are taught at an early stage of our apprenticeship, usually first year of graduate school, certainly by the time we start our theses, that we should not waste our time on problems and in questions that don't have definite answers. But artists often don't care what the answer is, because definite answers often don't exist in the arts. Ideas in a novel or in a painting are complicated by the intrinsic ambiguity of human beings and the uncertainties of the human heart. the uncertainties of human psychology. They are why these uncertainties and contradictions and ambiguities are why the characters of a good novel can be debated endlessly. Why we react to Hillary Clinton or Barack Obama at a gut level. Why God held the apple in front of Eve and then forbade her to eat it. For artists, there are many interesting questions that don't have answers, like what is the nature of love, or what is the nature of God, or would we be happier if we lived to be 1,000 years old? These are terribly interesting questions. They're provocative questions. They stimulate our creativity, and yet they don't have definite answers or any answers at all. One of my favorite little books is Letters to a Young Poet by the German poet Rainer Maria Rilke, and he writes in that little book that we should learn to love the questions themselves, like locked rooms and like books written in a very foreign tongue. And I've come to learn that we need questions with answers and we need questions without answers. Both kinds of questions are part of being human. Well, I've been speaking about some of the differences between the scientists and the artists, and I wanted to talk now about some of the many similarities. And first of all, I think that both the scientists and the artists seek beauty. Beauty is a hard thing to define in any field. We're probably more familiar with the beauty that we talk about in the arts. My wife, the wife who grew up in Atlanta, is a painter. And when she talks about her painting and what she's trying to achieve, she uses words like simplicity of the design, or unity, or balance. You're probably less familiar with, being scientists and engineers, you may be just as familiar with the kind of beauty that we have in science, but let me refer to a book by Steven Weinberg, a Nobel Prize-winning physicist, a popular book, in which he has a whole chapter. I think the book is titled Dreams of a Final Theory, and he has a whole chapter in that book titled Beautiful Theories. And one of the ideas that Weinberg and other physicists associate with beauty in scientific theory is simplicity. That's a word that Weinberg uses, the same word that my wife uses. But when scientists talk about simplicity, I know this is what physicists mean, they're really talking about simplicity of ideas. Einstein's general theory of relativity, for example, his theory of gravity, hinges completely on one simple idea, which is that gravity is equivalent to acceleration. And with that one idea, Einstein erects his entire theory with all of its complex mathematics. Another quality that Weinberg talks about that makes beauty in a scientific theory is inevitability. You've all seen paintings or heard musical compositions where you felt that not a single brushstroke or a single note could be altered without changing the whole. And the same is true in science. The same is true of Maxwell's theory of electromagnetism or Einstein's theory of gravity, that if you changed one thing, you would destroy the entire theory. There's a certain kind of necessity and inevitability that is part of the beauty. And I would argue that's the same in both the sciences and the arts. Let me turn to the concept of truth. I'm sort of going through the Platonic ideals here. The folklore is that novelists make up everything and physicists make up nothing, or I should say scientists make up nothing. And both views are false. as all of you here know very well, creative imagination and inventiveness are hallmarks of the great scientists and the great engineers, just as those qualities are hallmarks of the great artists. And I would argue that on the other side of the coin, that artists, and I can speak most certainly about novelists, have to conform to a large body of recognized truth about human nature. Theoretical physicists especially work in a world of the mind. It is an abstract mathematical world. It's a world where models of reality are simplified into balls swinging on strings, where equations can be written down to describe the world. And in this abstract world that physicists create, there is a lot of imagination that goes on. Einstein used the word free invention of the mind when he described his process, and he said that you can't really find the truths of nature just by close observation and experiment, as you would think the scientist does all the time. But instead, you have to start from your own imagination, start with a mental construction, find a theory out of your own mind, work out its consequences, and then test those against experiment. A type of scientific process that I think that a lot of non-scientists would find surprising. And one of the greatest examples of this free invention of the mind of Einstein was his work on the theory of special relativity, his theory of time. And there, as all of you know who have taken physics, he begins with this astonishing, outrageous postulate that the speed of a light ray is the same whether you're running towards the light ray or away from it. It comes at you at the same speed whether you're running towards the light ray or away from it, which makes no intuitive sense whatsoever. You know, if there's a car coming down the street and you run towards the car, it comes at you at a faster speed than if you run away from the car. But Einstein said if this is a light ray, it comes at you at the same speed either way. And Einstein realized that our physical intuition about the way nature behaves could be very wrong when it comes to high speeds. He was using his imagination to make this postulate for other reasons that had to do with symmetry arguments, arguments that came right out of his mind. A more recent example of the use of invention in physics is string theory, which is the hottest topic in physics for the last 30 years, I just say theoretical physics. And in string theory, physicists propose that the smallest elements of nature are not subatomic particles like the electron, but tiny one-dimensional loops of vibrating energy called strings. And from these vibrations, all of physical reality comes out. All of the subatomic particles and forces and everything are different notes on these little violin strings. And there's one other aspect of string theory that's required by the theory, that instead of having 3 spatial dimensions, length, breadth, and width, that there are 9 spatial dimensions. There are 6 additional dimensions that we don't see because they're curled up in ultra-tiny loops. To date, there is no experiment that we know that's capable of testing string theory, and in fact, there's no experiment that we can imagine in the foreseeable future. Yet some of the best theoretical physicists in the world are working on string theory, and I would argue that they are working in a way that's very similar to what artists do, creating and inventing out of their own minds. But of course, even when scientists are developing new theories, they can't invent everything. They can't make up everything. There's a certain body of truth that you have to conform to. You can't have a new theory of gravity that says that apples fall up instead of down. And Richard Feynman who was on my thesis committee at Caltech, put it very well in his little book, The Character of Physical Law, when he said that in science we need imagination, but imagination with a terrible straitjacket. So I would ask you, what is the terrible straitjacket of the novelist? What are the facts, like the apple falling down instead of up, that the novelist must conform to when the novelist is inventing? And I would argue there are facts that the novelist has to conform to. They are the behavior and the psychology of Homo sapiens. And I know that we have some psychologists in the audience here who can correct me when I go astray. But I would argue that this behavior represents a body of emotional truth that the novelist is bound by. And let me give you an example of what I mean by emotional truth. Suppose that the novelist has invented a character about 40 years old, a man married with children, and we'll call him Gabriel so that we can keep track of him. And Gabriel is a fellow who's, he and his wife have just attended a Christmas party. Gabriel is a man who's not too secure. When he first got to the Christmas party, he worried that he had insulted the housekeeper's daughter, and then a little bit later he's about to give an after-dinner speech, and he's worried that he's going to insult some of the guests with what he has to say. So he's somewhat insecure. But anyway, after the Christmas party, he and his wife leave, and they've left their 2 children with a neighbor in their own hometown. They've decided to spend the night in this village where the Christmas party took place, and they're going to a hotel room. They're walking. It's not far from the house where the party is, and it's beginning to snow outside. And it's been, Greta has been quiet during the evening, but Gabriel looks over at her as they're walking hand in hand and realizes that they've had a good life together, and he feels attracted to her all over again and hopes that she can forget about the household chores and the kids for a night and think about the love that they have shared together. So they get to their hotel room, and they walk up some winding stairs, and the stairway is lit just by candlelight, and they open the door and walk in. And by this time, Gabriel is burning with desire for his wife, Greta, and he wants her to respond to him with an equal desire. And instead, she begins crying. And he asks her, why is she crying? And she says that there was a sad song sung by a man at the Christmas party that reminded her of a young boy that she used to know long ago. And Gabriel begins to feel a dread in his stomach, but he keeps asking Greta about this boy. And Greta says he was 17, and he worked in the gas works, and he had large brown eyes, and we used to go walking together in the country. And Gabriel asks Greta, were you in love with this boy? And she says, we were great together at the time. And then Greta said, he died at age 17. And Gabriel says, what did he die of so young? And Greta says, I think he died for me. And Greta flings herself to the bed, sobbing. Well, I'm sure that some of you know that this scene that I've described is the last scene of James Joyce's famous story, The Dead. And the question I ask you is, how will Joyce end the scene? What will be Gabriel's reaction to what his wife Greta has just told him? Suppose that he shows no reaction at all. Well, we wouldn't believe this reaction. Or suppose Gabriel feels superior to his wife's long dead lover of the distant past. We wouldn't believe this reaction either, because we know that Gabriel is too insecure a character for that. The ending that Joyce actually writes is this. Gabriel realizes that his wife has loved this boy of the distant past more than she's ever loved him. And he also realizes that he's never loved any woman with the passion that she has just shown. And after that realization, all he can do is sag against the window, watching the snow come down and listening to his wife breathe as she sleeps, listening as if he and she were never man and wife. This ending we believe, and we know that it's true even in fiction, because it accords with our knowledge of human nature, with our own life experiences, and it causes us anguish. Both the novelist and the physicist are seeking truth. For the novelist, it's truth in the world of the mind and the human heart, and for the physicist, it's truth in the world of mass and force. In seeking truth, both the novelist and the scientist must invent. Both kinds of invention are important, and both kinds of invention must be tested against experiment. The tests in science are more objective and final. No matter how beautiful a scientist's theory is, like the circular orbits or like the parity conservation, that invention can be proved definitively wrong. A novelist's characters or story cannot be proven definitively wrong, but they can ring false with the reader and thus lose their power. And in this way, the novelist is constantly testing his fiction against the accumulated life experience of the reader. There's an experience that the scientist and artist share, a most extraordinary experience, very dear to my heart, and that's the creative moment. Creativity is a mysterious thing. I personally write in two places. I do my creative writing in two places. One is a place I go in the summer. It's a summer house on an island surrounded by the ocean, and from my writing desk I can look out windows on two sides, big windows, and see the ocean. I can see a pine needle covered path that wanders down the hill from my house to the ocean. And the other place that I write is a little storage room off my garage in my home in Concord, Massachusetts. And in that room, there are no windows at all. And when I look up from my writing desk, I see only a plaster wall about 6 inches in front of my nose. Both of these writing places have served me equally well as a writer, because after about 20 minutes, I have completely lost myself in the imaginary world that I'm trying to create. I've lost all sense of my body, all sense of my ego, all sense of where I am, what time it is, who I am. I could be anywhere. And I want to describe to you my first experience with the creative moment in science, which it has a lot of similarities. I found that most scientists do not write about their creative moment. Artists write about their creative moment, painters, musicians, novelists, but scientists rarely write about their creative moments. That's why they don't is a topic for another lecture. So I wanted to tell you a little bit about my first creative moment in just 2 or 3 minutes. It happened in my first research problem as a graduate student. I was working on a problem that had to do with gravity. It was a theoretical problem, so I was just using pencil and paper. And I had written down all the equations that I thought I needed to solve on about 20 or 30 pieces of paper. And then I hit a wall. I was making an error, a mistake somewhere, and I didn't know what the error was. And I kept trying to find my mistake, going over the equations over and over again for about 3 or 4 months, and I couldn't find my mistake. I was beginning to think that I didn't have what it took to be a scientist. I began living in my little graduate student office, sleeping on a cot there, eating dinner from cans of tuna fish that I kept in the drawer of my desk. And then one morning, after about 4 or 5 months working on this problem, I woke up at about 5 a.m. It was still dark, and I felt like my head was lifting off my shoulders. I was seeing into this problem in a way that I had never done before. And the one sensation that I had was feeling that I was right. And I think that's common to the creative moment. You have this sense of rightness. And the closest physical analogy that I have experienced to the creative moment is what happens sometimes when you are sailing a sailboat in a boat that has a round hull, a round bottom. And in a round bottom sailboat, the wind can lift you up out of the water if you have a very strong wind. So the boat is skimming across the water like a stone. And all of the friction due to the water drag goes to zero. And what it feels like, it happens very suddenly when you get lifted up on the plane, it's called. It feels like this great big hand has grabbed hold of your mast and just yanks you forward. It's an exhilarating, exciting, thrilling feeling. And that's the closest analogy I can come to what it feels like in the creative moment. And I'm sure that many of you have had this creative moment that I'm talking about. So this is what I experienced this day, this dawn years ago on my first research problem in physics. I woke up feeling that my mind was planing, and I tiptoed out of my bedroom afraid to bring the friction back. I walked into the kitchen and sat down with my many pages of calculations, which by this time were coffee stained and curled at the edges. And somehow I had gotten an insight to the problem, which was not by going from one equation to the next, but I was able to see through the whole problem and see the mistake I was making. And I had this feeling of wanting to be alone with the problem, but having no sense of myself, no sense of ego, no sense of time, just being in this state of pure seeing and feeling that I was right. And after a while, I had solved my research problem, and I got up from the table and walked out into the hallway feeling incredibly powerful, incredibly wonderful. And I heard a noise and looked up at the wall, and there was a clock there and said it was 4 p.m. in the afternoon. I wanted to say just a few more words about the process of creativity in the science and sciences and the arts. I was talking about this at dinner a little bit. Several years ago, I did a study of some of the great scientific discoveries of the 20th century in all fields: biology, chemistry, physics, astronomy. About 24 discoveries in all, such things as Max Planck's discovery of the quantum, or Otto Levy's discovery of the way that nerves communicate with each other, Watson and Crick and Franklin's discovery of DNA. And I found that there was a common pattern of creativity in most of these discoveries, not all, but most of them. And the pattern was this. First, the scientist has to have a prepared mind. And when I say scientist, I mean scientist and engineer. not distinguishing here between scientists and engineers. The scientist has to have a prepared mind. They have to have done their homework. They have to know the craft. They have to have the tools at their disposal. There are no examples that I know of great discoveries in the 20th century in science made by amateurs. So you have to have the prepared mind to begin with. Then the next step in the pattern is you have to get stuck. And I know a lot of students think they have failed when they get stuck, but actually getting stuck can be an important part of the creative process. It really stimulates the creative imagination in some mysterious way when you're stuck. And then finally there's a shift in perspective, and you see how to solve the problem. I think these are all ingredients of the creative process. I wanted to end with one more aspect of common ground between the scientist and the artist. And I've lived in these two communities now for 25 years. And that is that all the scientists and all the artists that I've known do what they do because they love it and because they cannot imagine doing anything else. This is a compulsion, and this compulsion is both a blessing and a burden. It's a blessing because the creative life is a beautiful life, and we're not all lucky enough to be able to live a creative life. But it's also a burden because when the call comes, it can be unrelenting, and it can drown out the rest of life. This mixed blessing and burden must have been the sweet hell that Walt Whitman felt when he realized for the first time at a young age that he was destined to be a poet. "Nevermore shall I escape," said Whitman. This mixed blessing and burden must be why the astrophysicist Chandrasekhar continued working in science until his 80s. Why Einstein, when he was very young working in Bern, Switzerland, was found one day to be rocking the cradle of his young son with one hand and doing mathematical calculations with the other. When a beginning poet wrote to Rilke and asked Rilke whether he should continue to write poetry, Rilke wrote back that he should write only if he could not write. Rilke wrote, "Search for the reason that bids you to write. Find out whether it is spreading out its roots from the deepest place of your heart. And ask yourself whether you would die if you couldn't write. And above all, ask yourself, in the stillest hour of your night, must you write?" The Nobel Prize-winning biologist Barbara McClintock once described her passion for science. She said, quote, "I was just so interested in what I was doing that I could hardly wait to get up in the morning. One of my colleagues said that I must be a child because only children can't wait to get up in the morning." Well, I wanted to end with just a couple of sentences to the students here, and I think that probably a lot of you are students at heart. I certainly feel like I am still a student. But to your students who are now embarking on a life of learning and research, that you should find something that you're passionate about. You might find it in the classroom, and you might find it in the shower, or taking a walk, or talking to friends. But find something that you really love, something that you feel passionate about, something that you feel compelled to do. And when you find it, hold on to it. Don't let anybody talk you out of it, because only with some passion is life truly worth living, I think, and only with passion are you really alive. Thank you.